Welcome to this presentation on key characteristics of I/O devices, presented by deeplearn. Let's delve deeper into the characteristics that define the performance and application of I/O devices. One of the most critical factors is the data rate. This is the speed at which data can be transferred. Devices like SSDs boast high transfer rates, while older technologies like floppy disks operate at much slower speeds. Next, consider the application of these devices. For instance, a high-speed network card might be optimized for data-intensive tasks like video streaming, whereas a keyboard is designed for minimal data transfer needs. Software must be tailored to the specific capabilities of these devices, impacting overall system design. We also need to address the complexity of control. The I/O module's architecture can significantly influence how the operating system manages device interactions. A simple device, like a keyboard, requires less complex control than a sophisticated disk drive with multiple read-write heads. Furthermore, data can be transferred either as streams or in blocks. Streaming is often used for real-time data, such as video playback, while block transfers might be more common in file storage operations. Lastly, error handling varies widely among devices. For example, while a printer might simply jam, a disk drive could suffer from more complex errors like data corruption. Each device has specific error reporting and response mechanisms, which an operating system must interpret effectively to maintain performance. How do you think different error handling strategies impact user trust in technology? Now, let's examine the techniques employed to handle I/O operations, each with its advantages and drawbacks. The first is programmed I/O, where the processor directly issues commands to an I/O module and then waits for the operation to complete. This method can lead to inefficiencies, as the processor is effectively idle during the wait time. Imagine sitting in traffic without moving. In contrast, interrupt-driven I/O allows the processor to continue executing other instructions while waiting for the I/O operation to complete. This approach significantly enhances system responsiveness. When the I/O module is ready, it sends an interrupt signal to the processor, which then pauses its current task to handle the I/O operation. Direct Memory Access, or DMA, takes this a step further. A DMA controller can manage data transfers between the main memory and I/O devices without processor intervention, which frees the CPU to perform other tasks. This is particularly beneficial for high-speed data transfers, such as those needed for video processing or large database operations. However, as we design systems, we must consider efficiency and avoid bottlenecks that can slow down overall performance. Each of these I/O techniques offers trade-offs between simplicity, control, and performance. For instance, while DMA can improve efficiency, it adds complexity to the system. Which I/O technique do you think would be most beneficial in a high-performance computing environment, and why? Next, we focus on disk I/O performance, an area critical for overall system efficiency. Access time is the total time required to perform a read or write operation, and it is influenced by both seek time and rotational delay. Seek time refers to the duration needed for the read-write head to move to the correct track on the disk. This movement is inherently mechanical and can vary based on the disk design. Innovations in disk technology have reduced average seek times, but they still represent a significant portion of access time. Rotational delay is another critical factor, representing the time it takes for the desired sector of the disk to come under the read-write head. Modern hard drives can spin at speeds over 15,000 RPM, significantly reducing this delay compared to older drives. Once the head is positioned, data transfer time kicks in. This is the actual time required to read or write the data once the head is in place. It's important to optimize all these parameters because disk I/O operations often form a significant bottleneck within computing systems, especially in data-intensive applications. Understanding these performance parameters allows developers and system architects to design more efficient storage solutions. For instance, RAID configurations can be employed to enhance read-write speeds and redundancy. How do you think advancements in SSD technology could further change our approach to disk I/O performance? Let's explore various disk scheduling algorithms, which play a crucial role in managing I/O operations effectively. The simplest method is first in, first out, FIFO, where requests are serviced in the order they arrive. While this method is fair, it can lead to inefficiencies, especially if a request at the end of the queue is time sensitive. Shortest seek time first, SSTF, improves upon FIFO by prioritizing requests that require the least movement of the disk arm. This algorithm can significantly reduce average seek time and improve overall throughput, but it may lead to starvation for requests that are much further away. The scan algorithm, often referred to as the elevator algorithm, moves the read-write head in one direction, servicing requests until it reaches the end of the disk, at which point it reverses direction. This approach balances fairness and efficiency as it services requests in a more organized manner. C-scan, or circular scan, enhances this further by only servicing requests in one direction and quickly returning to the starting point without servicing requests on the way back. This method can lead to better wait times for requests located at the outer tracks. Each of these algorithms presents trade-offs between fairness and performance. For example, while FIFO is simple, it does not consider the urgency of certain requests. In what scenarios would you prioritize fairness over speed in disk scheduling, and why? Finally, we arrive at RAID, or Redundant Array of Independent Disks, a technology that enhances both data reliability and performance. RAID configurations range from 0 to 6, each offering different trade-offs between redundancy, performance, and storage efficiency. RAID 0 employs striping, distributing data across multiple disks to improve performance significantly. However, it offers no redundancy. If one disk fails, all data is lost. This configuration is ideal for applications where speed is critical and data loss is acceptable. In contrast, RAID 1 uses mirroring, duplicating the same data on two disks. This provides excellent redundancy. If one disk fails, the other can take over without data loss. However, the downside is that it effectively halves the available storage capacity. More advanced configurations like RAID 5 and RAID 6 utilize distributed parity, allowing for fault tolerance while also maintaining performance. RAID 5 requires a minimum of 3 disks and can tolerate a single disk failure, while RAID 6 can handle 2 simultaneous disk failures, making it a robust choice for critical data storage. The implementation of RAID highlights the balance between performance and data integrity. As we think about future developments in storage technology, how do you envision RAID evolving in response to the growing need for large-scale, reliable data storage? This format provides a structured approach to the topic of I/O management and disk scheduling, facilitating a comprehensive and engaging learning experience for college students. Each slide builds on previous knowledge, fostering a deeper understanding of the subject matter. Thank you for watching this presentation.